Hello students, and welcome back to my videos on spectroscopy. In the first two videos, we talked about the theory of NMR. And today, we're transitioning to learning how to read NMR. So this is NMR lecture number 3. Here's a quick review of what we talked about at the end of the last lecture. So this is the basic idea of how NMR spectroscopy works. Remember, you have your light source, your sample, and your detector. And first things first, we take a sample, we put it in a magnetic field. There's our magnetic field. When that happens, remember, we're looking at the hydrogens. All of this is about looking at the hydrogens. It's true that in organic compounds, there's going to be carbon. Oftentimes, there's oxygen or nitrogen or a halogen. All that stuff is in there, but we are not observing all of those other elements. In this type of proton NMR, all we're looking at is the hydrogens. So the other atoms are just hanging out, but the hydrogens are the ones that line up either with the field or against it. So this little black arrow represents a hydrogen in the same direction as the magnetic field. Now we're going to start shining light on it. And remember, if we want this hydrogen atom to resonate, to flip up and down, we have to hit it with the right resonant frequency. And that's going to be somewhere in the radio range. So we shine light on it. If it's not the exact right frequency, nothing happens, and the light passes through to the detector. And the detector is like, hey, I see some light. Then if you tune this light source, adjust it so that it sends out a slightly different frequency in the radio range, eventually, if you tune it enough, you'll see some resonance. Remember, the resonance frequency is directly proportional to gamma times b net over 2 pi. These are just constants. So the frequency is proportional to the strength of the magnetic field, the net magnetic field that hydrogen's feeling. Once we hit resonance, oh, look at that arrow flip up and down. Do you see it? When that happens, of course, it's going to absorb some of the light. And when it absorbs some of that light, the detector's like, hey, here we are, we're on resonance. And it will record that particular frequency, right? The computer will match all those things up. And this is an example of a really, really simple NMR spectra. So today we're going to talk more about how to read these NMR spectra, both the simple ones and ones that are a little bit more complicated. So on to that. Let's talk about this. For all of these spectra, and if you want, you can get out some of your packets and sort of have a look at those. We're going to start with the packet that says NMR sample spectra. If you got a packet in the mail, it's the one with the blue cover. And also, why don't you grab out that yellow sheet that says sample proton NMR chemical shifts. It's just one page. So get out your blue NMR sample spectra and your yellow sample NMR chemical shifts. I'll hold on for a second, just hit pause, and then come back. Okay, so let's have a look at this. First of all, I want to just sort of give you a little bit of frame of reference and some context for this. Okay. NMR spectra are by convention read from right to left. So go to the right-hand side there. You know, in English, we're oftentimes usually reading from left to right. Here we're going to read from right to left. This is for historical reasons, which has to do with how these instruments were first put together and how the pages would unspool and how the pens would write on them. But we never changed. So we're still reading from right to left. So you see on the far right is 0. And the numbers increase as you go left. The X scale on the X-axis is not in hertz or megahertz, which you might think, because remember, what we're looking at here are frequencies, but actually in a unit called parts per million. The parts per million unit will let us be able to sort of compare apples to apples, right? So remember, the frequency is directly proportional to the net magnetic field that those hydrogens are feeling, and different universities, different scientific organizations or companies are going to have magnets that are slightly different strength. You know, that powerful electromagnet is going to be slightly different from instrument to instrument. So in order to be able to compare one spectra to the other, we convert the frequency into something called parts per million. So don't worry too much about this, but just understand that that's what those numbers are. They're parts per million difference of the frequency, of the resonant frequency. You'll remember that when we talked about B local and B applied, B local is caused by the electrons circulating. Those are the differences between different compounds. So what separates water from methane, from propanol, is that their B locals are slightly different because the electron structure of those compounds is slightly different. That B local is really, really, really tiny compared to that powerful electromagnet that's generating B applied. So those little local differences are like a million times smaller, right? And so when those Larmor resonance frequencies vary by 1/1,000,000th or 2/1,000,000ths, they're going to show up 1 unit apart or 2 units apart on the spectrum, right? So that's why we're using ppm. 0 does not mean that the frequency is 0, right? The frequency of 0 would mean there's no energy, there's no radio wave at all. 0 in the spectrum is arbitrarily picked as the location of the Larmor frequency for a very specific compound. And the compound we use is called TMS, or tetramethylsilane. So here's an example of TMS. TMS is a silicon atom with 4 methyl groups stuck around it. You'll see that TMS has lots of hydrogens, and as we'll talk later, these hydrogens are all magnetically equivalent. So they all give rise to the same signal. So right before you're going to start doing an NMR experiment, you'll take a big test tube with your sample in it, and you'll add 1 drop of tetramethylsilane. And then you'll put it in your NMR instrument and take a reading. And what you'll see is right at 0, there'll be a little tiny peak right here. It's not actually shown on all of these spectra that we'll be looking at. But in real life, there'll always be a tiny little peak at 0, and you adjust your spectrometer such that 0 falls exactly on that little peak that's caused by tetramethylsilane. And then the rest of your sample should appear somewhere sort of out here to the left. So if you see a tiny little peak at 0, ignore that and look at the rest of the spectrum. That's just your reference compound, TMS. Okay, let's talk some more about what we're looking at here on the spectrum. To the right, when you see signals or peaks to the right, those have more shielding. And what do we mean by more shielding, right? Remember, what we're looking at is the difference in Larmor frequency, and that's caused by compounds that have different amounts of B local. And B local is caused by electrons zooming all around. So if you see peaks further to the right, those are ones that have more electrons around the hydrogens. Those are compounds where the hydrogens exist in electron-rich environments. So the shielding we're talking about here is electron shielding. When those electrons zip all around, they're creating a bigger B local, and that B local cancels out some of the B applied to make the B net smaller. Right? And here's what I just said, right? So as you have more electrons spinning around, it will shield some of the applied magnetic field because B local is bigger and therefore B net is smaller. Why do we use TMS for our reference standard? Well, because of the silicon atom, TMS has a whole lot of electron shielding. There's lots of extra electrons buzzing around there, and they create a signal that's pretty far to the right, right? With larger B locals, that means smaller B nets. So TMS has the smallest B net of any common organic compound that you might find. Also, TMS is relatively unreactive, so it won't react chemically with anything that you might be putting in your test tube, right? You don't want your reference compound to destroy that precious aldehyde or acid or ether that you made. So again, TMS, you won't always see it, but if it appears as a little peak close to 0. So as we said, TMS has a relatively small Larmor frequency because it has a big B local, small B net. So the same thing as you go to the right, that's more shielding. Those are also where you find things that have smaller Larmor frequencies, of course. Those are 2 different ways to say the same thing. And we also call that, again, for historical reasons, which we're not going to talk about here, we call that direction upfield. So upfield is to the right, towards TMS. Those are compounds with more shielding, more electron-rich environments, smaller Larmor frequencies because they have smaller B net. And conversely, as you move to the left, it's all of the opposites of those things, right? So as you move to the left, we call that downfield. Compounds or hydrogens that appear downfield are going to have less electrons buzzing around them. Less electrons or fewer electrons means a smaller B local, which means a larger B net. And remember, B net is directly proportional to the Larmor frequency. So as you go to the left, you get larger Larmor frequencies, less electron density around the hydrogen. We call that direction downfield. Here's a question for you. We don't normally find sort of isolated H pluses all by themselves. This would be, kind of what makes an acid an acid. But if we were to find one and we were able to capture it and stuff it into an NMR instrument, where would you find a lonely H plus with no electrons at all? Pause the video and think about this for a minute, and then we'll discuss. An isolated H plus, of course, is going to have no electrons around it at all, which means in terms of shielding, right, it's going to have not just less shielding, but no shielding at all. It's going to have literally no B local, which means B net is at a maximum, which means the Larmor frequency is at a maximum, and it would be way the heck downfield, like, probably at 20 or 25 or 30, so way off the screen someplace. Let's talk about chemical shift for a minute. So again, typically you find the compound we're looking for in the upper left-hand corner of most of these practice NMR exercises. I've put a little sample here too, model. This is, of course, methane. Methane has a chemical shift around 1, or actually maybe 0.9 ppm. This is methane, except we've replaced one of the hydrogens with a chlorine. Because we've replaced it with a chlorine now, that chlorine is going to pull electron density towards the chlorine and actually away from the hydrogens. So as electrons get sucked away from the hydrogens, there's now actually less shielding around those hydrogens, less electron density. Sort of what we're developing a partial positive charge here, and that's going to push the signal to the left, which remember is downfield, right? So 1 chlorine is going to push my signal down to about 3 or 3.1 ppm. What would happen if I added more chlorines, right? This is 1, 2, 3 chlorines. Oh my goodness, now they're really going to draw electron density away from that hydrogen. And as a result, the signal for this hydrogen is going to be shifted even further downfield, down here. So a couple things to note here. Number one, this one has actually fewer hydrogens than this one and this one. So in real life, if we hadn't adjusted our machine, this bottom peak would actually be a little bit shorter or smaller, because this bottom peak is only showing 1 hydrogen, whereas, for example, this top peak represents 4 different hydrogens. So as we'll see later on and discuss later on, the more hydrogens you have, the bigger the signal that you're going to see. So that's not reflected here. But something that you should notice, if you have your yellow sample proton NMR chemical shift handout, please grab that out. One of the things that you notice up at the top where it says primary, that's if you have a hydrogen attached to a carbon where it's on the end. And of course, methyl is even one step above primary. But look over there where it says chemical shift. It has that little funky delta symbol. Delta is the abbreviation or symbol for chemical shift. And of course, ppm in parentheses, that's the unit we're talking about. So the unit is ppm. That little lowercase Greek delta is the symbol for chemical shift. And that tells you how far this sample is shifted away from TMS, right? So on your yellow sheet, it says 0.9 ppms. And of course, if you look at methane, and where it appears is somewhere around 0.9 to 1 or so. So that makes sense. Look at your sheet again and find chlorides. Find chlorides. It's about halfway down, not quite halfway down. You can see it's a hydrogen bonded to a carbon, and that carbon has on it a chlorine. And if you look to the right and see what the chemical shift is on your sheet, it says between 3 and 4. And sure enough, when we look at chloromethane, right, our chemical shift is between 3 and 4 for this signal. That's for 1 chlorine that's attached. Now, by the time we get to 3 chlorines, of course, 3 chlorines is going to have more of an effect than just 1 chlorine. Notice that the chemical shift is not triple, right? Triple 3 to 4 would be 9 to 12. So it doesn't increase linearly like this, but it's always the case that if one functional group has a chemical shift of, let's say X, that if you have multiple of those chemical shifts or multiple of those groups, the chemical shift is always going to be bigger than X, right? In other words, you're always pushing things downfield because pretty much all functional groups are going to be more electronegative than carbon and hydrogen. And because they're more electronegative than carbon and hydrogen, they're going to suck electron density away and they're going to push things further downfield. But you can't just like multiply by 2 or multiply by 3. It's not quite that simple. So here is our chemical shift. Let's actually make sure that we get a good definition for chemical shift. We've been talking about this a lot. But again, here's that symbol, the lowercase Greek letter delta. But chemical shift is how much the resonant frequency of a nucleus is shifted away from our standard. And for our purposes, the standard is always going to be that compound TMS, which will appear at 0. Right? So it's how much is the Larmor frequency, how much is the resonance frequency shifted away from TMS. And the unit for chemical shift is going to be in parts per million. Most organic functional groups have a characteristic chemical shift. Usually it's a range because different organic compounds are slightly different. Even if they have a chlorine, they're still, how that affects the electron structure is going to be a little bit subtle and a little bit different. By the way, this yellow sheet is not going to be something that I ask you to memorize, right? So you will always, 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 always be able to use on any homework assignment, any assessment, any test, any quiz, anything, you will always be able to use your table of standard proton NMR chemical shifts, right? And by the way, if you have looked at the back of that, if you flip over to the back of that table, it's the exact same information, but I just organized it in a different way. So on the back, I sorted it by chemical shift from small to big. So sometimes that will help you find something. If you're like, you have a signal that's between, say, 3.5 and 4, and you're like, what could that be? The back can help you. Now, I will caution you, though, that the back is not comprehensive because, for example, the one we just looked at, this one, right, doesn't appear anywhere on there. This is a chemical shift between 7 and 8. It's created by chlorines. You will not see that anywhere on the back of your table because this is for 3 chlorines. Right, so be a little bit cautious in using the back of that table. Right, just because it's not there doesn't mean that it's not there, so to speak. So I usually use the front, right, where it says organized by structure. Okay. Yeah, and as an example, right, an H1 nuclei on a carbon atom that also has a chlorine typically exhibits a chemical shift of 3 to 4 ppm downfield of TMS. Right, chemical shifts are always downfield, unless they're negative, which we'll talk about maybe never. All right, so here again is that information. You can find this anywhere. There's lots of tables online, but if you want to use the table that I gave you, you can also, of course, find an electronic copy on PowerSchool. Oh, there's my kids. Wait, it looks like my son has a question. He said, oh, here we go. Which hydrogens have bigger chemical shifts, CH3F or CH3I? Well, what do you think? Take a minute and ponder that. Just if you had to guess without looking it up, which one has a bigger chemical shift? And Piper says, well, that's actually pretty easy. CH3F on average, right? Remember, F is more electronegative than I. So because it has a bigger pull on electrons, it's going to suck more electron density away from the hydrogens. They're going to have a more partial positive charge in the CH3F. Therefore, you're going to see that signal down to the left. And when you actually look that up on the table, fluorides are between 4.1 and 4.6 typically, and iodides are somewhere between 2 and 4. So kind of makes sense. All right. Oh, wait, looks like there's another question. Oh, here we go. Which H's have a bigger chemical shift? CH3OH, so that's methanol, or CH3COOH, ethanoic or acetic acid. So this one's near 2 O's. This one's near 1 O. What do you think? Make a prediction. Which one do you think is going to shift further to the left? All right, maybe you guessed, maybe you looked at your table, maybe you're just waiting for the answer. Oh, interestingly, it's CH3OH, right? It's methanol. Anders says CH3OH. I would have guessed the other one because, there's more O's and stuff. Yeah, okay, well, that's maybe a good guess. So here's the bottom line. Sometimes your intuition about chemical shifts is correct, and sometimes it's not. So the bottom line, you need to use your table, right? I don't know why she calls them turd bucket. It's not very nice. I'm giving you this table of sample proton chemical shifts for a reason. Please use that and look things up. I'm not expecting you to memorize these things. Don't guess, right? Use all of your gifts, all of your tools. All right, in our next video, we're going to talk about another phenomenon called spin-spin splitting. So stay tuned for that.